There are many types of energy, but in a problem, they won't just tell you the block has kinetic energy. What do we look for? If the object has speed, then it has kinetic energy. If it has height above some zero level, then it has gravitational potential energy. And if there's a spring or an elastic object that we've compressed, then it has elastic potential energy. These are the three forms of energy, and this is what we look for. They're not going to say, the block had potential energy. They're going to say, the block is at a height of 12 meters above the ground. In addition, we also have to look for friction. If there is work done by friction, we know that we have to consider negative force times distance. Why is there a negative sign? Well, imagine that you've got a block sliding to the right. Where would friction act? It would oppose the block's motion. Or maybe instead we've got a block sliding to the left. Where would the friction act? It would oppose the block's motion again. But it doesn't have to be kinetic friction or surface friction. Imagine you take a ball and you throw it upward into the air so it travels up. Gravity acts on the ball, but there might be air resistance. Air resistance is a form of friction. It dissipates energy, and it would oppose the block's motion, just like this case. So air friction would point down. Or if you take a ball and you drop it from some height, the ball would travel down, and where would air friction point? Air resistance? The opposite way. In every one of these scenarios, look at the angle between the force and the distance, because after all, work is force times distance times the cosine of the angle between that force you've chosen and the distance. So we're talking about the friction force, the work of friction. So what is the angle between the friction force and the distance? Here, it's 180. Here, 180. 180, and you guessed it, 180. And the cosine of 180 is always negative 1. That's where this negative sign comes from. In the problems, we're going to have an object that's moving from one configuration to another configuration. And the amount of energy that you have at the beginning, maybe it's 10 joules, has to equal the amount of energy you have later at the end. If you start with 14 joules, you have to have 14 joules at the end. That's conservation of mechanical energy. The only exception, let's say you start initially with 10 joules, and friction takes away 2 joules. You would have to add the work done by friction, the negative 2 joules. Or maybe you start with 13 joules, and air resistance takes away 5 joules. It does negative 5 joules of work. We would have to add the work from friction. But maybe it's not friction. Maybe you've got a block sliding around on a table, or an air hockey puck, and sliding around on the table, and you come in and you give it a push every now and then. Well, if you start with 5 joules in the system, and you do positive work, positive 3 joules, that would give a final energy of 8. So what we're noticing is that you have to take the initial energy and add the external work from non-conservative forces, and that gives you the total final energy. We're adding the work that's done because when you do work, you modify how much energy you started with, and you have to add the modification to get to the final. Let's run through a few different scenarios. We have something like this, and there's a marble at the very top. And the marble rolls down, and when it rolls back up, it only gets this high before it turns around and comes back down again. How can we analyze this using energy conservation? Well, you have to identify where it starts and where it ends. At the beginning, do we have speed? Well, no. It starts from rest, let's say. At the beginning, do we have height? Yes. We have to choose some 0 level. We'll measure height from here. And there is a vertical height. At the beginning, do we have any compression of a spring? No, there's no spring whatsoever. At the end, we run through the same 3. There's no speed because it's at the peak. It turns around and it stops briefly when it reaches the peak. There's height. Yes, there is height. At the end. And there's no compression of a spring still. So we can distinguish by calling these H initial and H final. How do we set up our energy equation? On the left side, we add the initial energy. And because there's height, we have to add potential. So we have initial potential energy, and at the right side, we have final potential energy. But of course, the reason that the thing doesn't go as high is because friction does some work, so the problem would say that. That's how we construct the equation. We can then use the equation, the actual formula for potential energy, mgh initial plus the work done from friction, maybe we need this, equals mgh final. And the problem will provide you with mass maybe, and maybe we'll know g, maybe they'll tell us the initial height, and they'll tell us how much work is done, and then we have to find the final height. Or maybe they decide that they're going to give you the final height, we know g, they're going to give you the mass, they'll give you the initial height, and you have to calculate how much work friction does. One of the things from the equation will be the unknown. So let's go through each of these scenarios. We start with a pendulum located at this height. We let it go from rest, and it swings down to the middle. We want to know how fast is it going at the bottom. Well, we look and we say at the beginning, there is no speed, it's released from rest. At the beginning, there is height, but there's no compression. So all we have initially is height. And at the end, we have reached the bottom, we have reached the 0 level. So there is no height. There's none of this. There's no compressed spring, but there is speed. It's moving now. So we've got some speed here, V final. So when we set up our equation, we would say we start with gravitational potential energy, and that converts into kinetic energy, or mgh initial equals 1/2 mvf squared. If they told us that there was friction acting or air resistance, we would just add in that negative work right there. The next one, we've got 2 springs, and one of the springs is on the left side, one is on the right side. A block is pushed up against the left spring, it releases, it travels across, it strikes the other, and compresses that spring. Now we're showing the block here when it has it's reached maximum displacement on the spring. So the spring has been pushed in as far as it can go. It can't get pushed any farther. That's the best the block can do before the block goes flying off again. So the block won't stop forever here. It's about to go flying off. We're only considering from this initial moment to that final moment. So what do we start with? We run through the checklist. There's no speed. There's no height. It's not above the ground. And what about compression of a spring? Yes, there's compression. So we start with compression, X initial. It's how far in we've pushed that spring. And then it rolls across, and at this final moment, there's no speed because that's the farthest it compresses the spring. There's no height, the block isn't up off the ground, but there is compression of the other spring. So we have here some compression, X final. So when we construct the equation, we say we have the spring energy, which is 1/2 k x initial squared, is converting into, again, spring energy, 1/2 k x final squared. where K is the stiffness for each spring. If there were friction being done, maybe as the block rolls across the surface, it has friction that it encounters. We would simply add in right here the work done by friction, which will come out negative. Okay, next one. We start with the block up above the ground. It travels down and over, and then it compresses this spring, so the spring has been pushed in. Now again, whenever we have compression of the spring, we assume that this is the farthest the spring compresses. So this is the last moment, right before the block goes flying off. The block is changing direction, it briefly stops. We start with height and nothing else. There's no speed initially, no compression. At the end, what do we have? Just compression of a spring. So to set up our equation, we start with the energy for height, that's mgh, gravitational, and it all converts into compression energy, 1/2 kx final squared. And if there were friction as it rolls across, as it slides across the surface, if there's friction, we just add in the work from friction, and it's negative. It's supposed to be an F. Okay, on the next one. Let's say you throw a ball upward into the air, and it travels to the peak height. We start with no height at all. We're at the bottom. But we have speed. And when we get to the top, it stops at the peak, but we do have height. So we begin with the energy of speed or energy of motion. That's kinetic. And we're converting it at the end. We convert it into mgh, gravitational potential energy. If there were air resistance along the way, we would just add that in, modify the left side of the equation. Next one, we've got a spring. You release the spring from rest. It's at rest at the top. I'm sorry, the ball. You release the ball from rest. It falls down and accelerates. It strikes the spring and it compresses the spring some amount, x. So initially, if we consider the bottom right here, consider that your 0 level. Initially, this thing has height above the 0 level. And it doesn't have speed, it's not moving. It does have height, but there's no compression on the left side. No compression at the beginning. Okay, so then at the end, what kind of energy do we have? We have, well, it's not moving because it's done compressing the spring. So there's no speed, there's no height because we reached that bottom level that we just marked with dotted lines. And we do have compression. So let's say there's x final. We're converting the energy for height. That's mgh. That's what we start with on the left side. At the right side, the final side, it converts into the energy of springs. 1/2 kx squared. And if there were friction, air resistance along the way, we would just add that work, modify the work from friction by adding it to what we started with. Of course, when I say adding, this work is negative, so we're really subtracting. Final one. You start with a block that is compressed. Okay, compression. Initially we have spring energy, but the block also has some height. See that? It's above the ground, it's above the bottom. And the block goes down and over, and now it's moving. Speed. There is no more compression, and there is no more height. We're at the 0 level. We're at the ground. So we start on the left side. We start with two forms of energy. Height, which is really gravitational potential energy. So mgh. And we have compression of a spring, so that's elastic potential energy. And what do we end with? Speed, and the energy of speed is kinetic energy. And again, if there were friction along the way, we would just modify how much, the friction would modify what we started with. It would change the initial amount, so we would have to add that to the left side.